All right, so the rest of these zero force members, I just handed this back. They're graded online for those of you online. 2 unloaded corners there, nothing else, just those. You got questions, you don't let me know on these.
I've got a question.
Yeah.
I'm very difficult. This is hard.
Yeah.
Oh, not that one. That one's easy.
Oh, that was easy.
I just meant on this assignment in general.
Yeah, I know, it is. I agree. All right, we good? Okay, this one you got one other zero right there. What we're looking for are unloaded corners and unloaded T's with 2 unknowns. That's really the only place you can prove that something is 0. Let's see, unloaded corners with 2 unknowns, unloaded T's with 3 unknowns, you might say. Okay. We're good with that one? Good. This one at D, you can see that that's 0, and at F, you can see that this one's 0. Unloaded T's, or unloaded T's if you consider that force to be a part of the T then. Okay. We good with that one? Okay. This one doesn't have any zeros.
That's a good question.
No, I kind of warned you on that. It was a trick question with a warning. I said some of them may not have any zero force members. Okay, we good? So no unloaded T's, no unloaded corners, basically. Okay. All right, this one is kind of, you work your way through. So if BC is 0, then BD is 0. And if BD is 0, then ED, there, DE is 0. And then we got FG, that would be 0 also, but EG would not because of the load at G, okay? So I'm looking at
FG is vertical.
FG, is it vertical? It really doesn't matter. What's going on here, if I'm up here, I can go sum of Fy prime and set that equal to 0. And it doesn't matter, whatever that angle is in there, whether it's vertical or not, and whatever this angle in here happens to be, that'll just be sine of whatever that angle is times FFG. So FG is 0. Even though it's pretty flat, it still doesn't make any difference. Right? Other questions on that? Okay, so basically unloaded 2 corners with 2 members, unloaded T's with 3 members, and I guess we can define that as being a T right in there, okay? We could just call the force one of the members. If we define them that way, it's pretty easy. We just got 2 things to be thinking about, okay? Okay. Okay, a little bit more to finish up with frames and machines here.
P1 doesn't transfer anything to F.
Let's see, P1, which one now?
P1 doesn't transfer anything to F because it's like that point at C stops it.
Yeah, you can get into the kind of the technical reasons for that. I find it helpful to think of these as having kind of looser joints on them, so to speak, so there's just a little bit of play. If C starts to move down, it's going to move down. If this is a little bit loose, that's going to start to sag, and there's no force there to prevent that. And so before that occurs very much, this thing, which does have supports on either end, is going to push back and say, no, you're not coming down. I'm not going to let you do that. So CF, EF don't do anything to prevent C from moving down, if you consider those joints to be a little loose, which is helpful when you're thinking about these. Okay, that's kind of the common sense reason why that force doesn't translate down into CF. Now, the more analytical reason to solve these, like, on homework or a test or whatever, is look at that joint at F. That is an unloaded corner. There is no Y force applied to that, so therefore to keep an equilibrium, CF has to be 0. So I tend to analyze these in a very analytic way. I discipline my thinking. I don't start thinking with common sense so much as I think very specifically. So we good with that? Okay. Any others? Okay. All right. Okay, a couple more of these frames and machines. This is on 590. I have a weird bolt cutter of some type, who knows? So we want to find the clamping force at G for this thing. So what I've done there is I've broken that thing up and I've exploded it up and I've taken a couple of the pieces out. Notice I decided not to deal with piece A, E, F, G because it's got too much stuff going on it. I don't think I could really do much with that with statics because there's just too many unknowns on it. Okay, so what I did, I took out B, C, E, and then D, F, G. That's how I decided to do that. They're smaller and I can handle them better. Okay, so I'm pushing with 90 newtons. Now, do you see any two-force members in there? We do want to get used to spotting those and pulling them out because you do have to find them to be able to analyze these things properly. Anything look like a two-force member? Yeah, I think so. 2 pins, no applied forces other than at the pins. So that's a two-force member. So when I see a two-force member, I apply it just as a force. I don't show it as a separate exploded piece of my views. I just show it as a force. Okay, so I imagine that CD is going to have to pull up on this to get that force exerted at G. So that means it's pulling, so it's in tension. So that means it'll probably pull down at C, right? Something like that. Okay. All right, now E is going to have 2 unknowns. It's just a pin joint. So something like that, as will F. F is just a pin joint. Okay. And then I'll assume this clamping force is just vertical there, perpendicular to the jaw. So there are my free body diagrams. Now I've got one force in common, so that's good. So I can jump that FCD right over there. Okay. So really what I'm going to have is starting left and working right is 3 unknowns on these things. So that's pretty good. I should be able to handle that. Okay. Okay. Now, what I want to do here is I want to think a little bit strategically here again. What I want to do is I want to get this one. That's my goal. And I know that I'm going to need, I'm going to take FCD and transfer it over. I know I'm going to do that. Okay. So if I got those 2, if I found FCD and I want to find this FG over here, how might I do that? Yeah. Yeah, I'm going to start there. I'm going to start here. I'm probably going to take a moment about E. I'm going to get FCD. I'm going to transfer that over. And once I've got it, I'll probably take a moment about F, okay? Now where I'm going with this is I'm not going to waste time finding EY and EX and FX and FY. They're not worth anything to me because I want to know what the clamping force is. They're not worth my time to find them, so I'm not going to bother with it. Okay, I'm just going to kind of get what I need.
David, is this stuff we're doing right now, I mean, I know it's important, is this for the test? Are we going to do this on the test or this is on the final more?
This is on the final.
Okay.
Yeah, the test ends at trusses. Okay. And I handed that review out. I'll cover that Wednesday. Okay. And if you got questions, I'll take them Wednesday too. I'm happy to do that. Okay. All right. So once I got the strategy, then off I go. So I'm going to do CE first. Sum of ME is 0. It's 3 times whatever FCD is minus 90 times 8 centimeters. So that gets me FCD, and that's 240 newtons. So if I push on the handle with 90, what I get on that FCD as it pulls down is 240. So what I've done, I've increased that force by almost 3 times, not quite, but almost. And that's the whole point of a lot of these gripping and cutting type things, is your magnifying force is what you're doing. Same thing with a jack, if you think about a jack, you're actually lifting your car with your own muscle power, okay? You're magnifying your muscle power to hold the car up. Now, what's the price you pay to lift? If you want to lift your car up 6 inches or something, what do you got to do to make that happen? Okay. I'm not waving at you. I'm demonstrating what would happen with a jack. Okay. What I'm doing, you got to move your hand much more than 6 inches to lift the car, because you're magnifying the force that you're pushing with. That's what you magnify with the machine, and the price you pay for that is you got to move your hand much more distance to lift the car 6 inches. So that's kind of how these things work. All right. So we good with that? Okay, and now we got there. See, I don't bother with EX and EY. They're not going to get me anything. I'm going to take that FCD and put it at that armature DFG. And I'll take a moment about F. So I'm going to have 9 times the 240 newtons. Now notice FCD was down here, pulling down. Now it's pulling up over there. That's that idea there on these frames and machines. You got to turn the forces around. Okay, I can take a moment about F and get the clamping force. 720. So I went from 990 up to 720. That's a factor of 8. So if this is a cutting device, if I wanted to cut through that pipe an inch, I'm going to have to move the handles 8 inches, is what's going on. I've got a factor of 8. Then I'm magnifying the force by 8, so I have to increase the distance by 8, a factor of 8. That's the deal. Okay. So we got any questions on that? Doing all right? Okay. So that's just a simple kind of cutting device or whatever it is. Okay. Okay. Now we got one more. It's a little different. This isn't quite the same as the frames and machines, but you analyze it in kind of a similar way, so we kind of throw it in there. It's rigging, okay? And you can take a whole class on rigging, on moving stuff around. I'm skipped a page, I'm on 597. There we go. So I've got kind of a fancy pulley system here, okay? And the idea is the same. I can cut down the force it takes to hold up that weight. I can make the force in the cable less than 600 newtons, okay, by rigging it. Now I want to find what force is required to hold up the block. Now what I want to do first is I want to identify how many ropes I've got. Because if you ever want to see some complicated rigging systems, look in a statics book. People who write these things get a little excited sometimes about these. They put in lots of pulleys and ropes all over the place. We'll keep them a little bit simpler and more practical, perhaps. So I can trace that rope around. That is one rope. Okay. Now, this is statics, and that's a frictionless pulley is the assumption. So what that means is the force in the rope is equal everywhere. Okay, so that everywhere in the rope has the same force in it. It's also a rope, it's a cable, so all it does is pull. So let's figure out the force in the rope. Now what I know here is I'm pulling with 600 newtons, so that's 600 newtons, as would this be, but I'm going to use the one on the top. That's 600 newtons. So I can put that down like so. So what I'm going to do is make a free body diagram out of that. And it's always helpful to show a boundary in a free body diagram. So my boundary will be like that, I think. If I'm going to cut that pulley loose, I'm going to take a free body diagram of that pulley is what I'm doing. All right. So how many ropes are pulling up then? There's 3, and they're all equal, right? So I think we can figure that one out pretty quick, what the forces are in the ropes. So I just cut through those 3 ropes, and they all have the same force in them, which I'll refer to as T for tension. So I can figure out pretty quick that the force on the rope is 200 newtons. Okay. So we doing all right with that? So what we're going to get here is if I go sum of Fy and set that equal to 0, what I'm going to have is minus 600 newtons plus 3 times whatever T is, and that's 0. That's the equation I generate for that. I called it F here instead of T, but you can call it whatever you like. So 3F minus 600 newtons is 0, so F is 200 newtons. Okay, now I'd also like to find the force on this pin at A. So I could, again, draw a free body diagram of that. So really what I would do for that free body diagram is pull the smaller pulley out. And what I've got then is I could cut that pulley out, kind of look at how the pin affects it. So really what I'd do would be to draw a free body diagram of that pulley. It would look something like that. So when you draw that diagram around that, remember, cables, what they do is they pull. So this one would pull to the left, and that one would pull down. So there's my 200 Newton forces, like so. And then I'm going to have those pin forces of the pin on the pulley pushing back. And I'm going to do equilibrium X and Y. Those pin forces are 200 each. So to get the force on the pin, which will depend a little bit on how the pin bracket's made and all that, but just simplistically, we could just take square root of some of the squares. You might be able to reduce that pin force by building a little different bracket style, but all the same, if it's a simple pin, it would just be square root of some of the squares. Okay.
Right, because the way the bracket is, it's like not symmetrical, so it probably would be pulling a little bit more down or left than I don't know.
Well, I mean, there might be all these practical considerations. I mean, you don't know, but here, that's creating a moment, but the moment balances. So there's kind of a net downward force. Yeah, at 45. Based on the information we've got, this is about as good as we can do with it, I think.
So for this pulley of A, since the rope in the Y direction is going down, it's pulling 200 newtons.
Yeah.
Do you automatic? It's going to be the equal amount in the negative X direction.
Yeah, these ropes.
That rope, yeah.
Yeah, this one's down,
Those
so
are
the
always
next.
going to be like equal to the
Yeah, right. So in statics, you assume that the forces in the cable is the same everywhere. If the sense oriented like that, it's down left with the rope, so the pin pushes up.
If you have a cable going around the pulley, it just bends the coordinates. So if you have like whatever going this way.
So even if it was like they're both pointing down, that's both.
Well, if they were both pointing down, you could have that, but then it would be like that.
Yeah.
Okay.
And then it'd be 400 newtons pushing back up, right, to hold it in equilibrium. Okay.
Yeah.
So I find it helpful to draw a boundary. That way I can kind of get a picture that I can draw. Yeah, question.
So the magnitude of A, what force is that? 283, what does that do?
Okay, what's happening here is you've got these two forces with 200 doing that. Kind of what I'm looking at is how A is pushing back. A is the resultant of those two, so A's doing that at 283. Because, we got to do the vector thing because they're X and Y directions. Okay. So, we good with that?
Did you found the magnitude of
Yes. Yeah, theorem of Pythagoras.
it? Okay.
Because they're X and Y, so I could use that theorem of Pythagoras. And again, that assumes a very simple connection between the pin and the pulley. Okay. So that's a couple applications for equilibrium. The first one was trusses. That'll be on the midterm. This next one here is frames and machines. That'll be on the final. That's down the road a ways. Okay. So we're kind of pulling things out and using our equilibrium stuff to analyze them. That's what we're doing. Trusses are fairly simple because it's just some of fx and some of fy generally, unless you do sections. Frames and machines get more complicated. Okay.